All right, so here we go. This is our, what is this, week 5 of remote learning. It's kind of a bummer that we couldn't be doing a lot of this in class together, obviously, but we're going to make the best of what we can. Now, if you guys are having any questions, I've been seeing a couple of questions. I'll address this right off the bat. A couple of questions come through on the homework assignments. I'm sure you've noticed I don't normally get to those until everyone has submitted them, which is Friday at midnight. So if you have questions on the homework, I know there's a comment section on the assignment itself. That's fine. You can leave a comment there if you wanted to, but also email me. If you email me, I can throw together a quick little 3-4 minute video walking you through something that's really been stumping you, before Thursday or before Friday. That way it kind of can help you guys out a little bit more, and I'd love to be able to do that. I just haven't been getting questions this last few weeks, and I've been noticing 1 or 2 random ones that have snuck through that people are just attaching to the homework. So that being said, we're going to talk about light a little bit more. This is actually going to be where we end the year, is talking about light. We've got a couple different aspects of it that we're going to break up into these last couple of 3 weeks, I believe. In this one, we're going to be primarily talking about what light is, how we measure it, and where it comes from. And so that's what we're going to be doing here today. So light is a wave. We're going to cover these 3 topics: atomic emission and absorption, spectral lines, the electromagnetic spectrum. This is simply, qualitative. What are they? How do we know that these things exist? It'll explain a little bit more about that whole universe expanding thing we talked about briefly at the end of last week. So what we know so far. What we know so far about waves in general: sound is a traveling longitudinal pressure wave, propagates outward from a source, has to travel through a medium. It is just a vibration that goes from one molecule to the next. So there has to be another molecule in that series of dominoes, if you will, to transfer that energy, transfer that vibration from place to place. With all that being said, we can measure wavelengths and frequencies, and we interpret those as the pitch of the sound being made, amplitude, or its displacement from where it would have been normally had that vibration not traveled through is going to be your volume. But then we also know that it has a Doppler shift. And the reason we connected light and sound with Doppler shifts last week is because both light and sound undergo this weird Doppler shift. Now, light behaves the same way. It has the same property of a wave in terms of being influenced by the Doppler shift. The only difference is that you have to be moving fast enough for that Doppler shift to even be noticed. To put this in perspective, for you to even notice a change in color, to put this in perspective, when we're talking about changes in sound, the average car is moving, let's come up with a random number, 75 miles an hour, which is roughly 30 meters per second. So that sound, or any sound coming from a vehicle traveling at 75 miles an hour, 30 meters per second, is moving at about 0.1% the speed, or no, 1% the speed of sound. Right? The speed of sound in the air is 340 meters per second. If you're moving 30 meters per second, that's about 1%. Put that in perspective to light, that same speed, 30 meters per second, would be less than 1/1,000,000th of the speed of light. So driving down the road in your car, you're not going to notice things changing color the way you hear things changing frequency of sound, because you're going nowhere near that upper threshold that possible wave could move through. Even putting it further in perspective, the fastest man-made object ever built, assembled, or launched is the Juno spacecraft that was sent to check up on and do some research on Jupiter in 2011. It was moving 165,000 miles an hour, which still was less than 1,000th or 1/10,000th of the speed of light. So even that one probably wouldn't have noticed a measurable Doppler. You could measure the Doppler shift, but it wouldn't be enough for us as humans to notice, for us to be able to see. So you get the Doppler shift occurring in both sound and light, and that was the big connection between those 2 things. That's what I wanted you guys to be able to at least understand. Now we're going to talk about how we know Doppler shifts in light occur if we can't actually, I guess you could say, see them with our own eyes. We have other instruments we can use to observe them. So that makes sense for sound, those Doppler shifts, but for light, it gets a little weird. We know Sound is a vibration propagated outward from a source through a medium. Light, on the other hand, still has to, because it's a wave, transmit some sort of energy. It has to be a physical disturbance as it travels from point A to point B. But what is it that's moving to cause light itself? I wouldn't expect you to be able to guess it, but it's something we have talked quite a bit about. It's the electron. And it all comes back to the electron and some of the weird things the electron does. I'm not saying this is the sole source of light in the universe. Photons can be generated from other reactions, like nuclear reactions occurring inside of the sun and a few other things, but visible light, the things that we're going to be talking about, the things that make your t-shirt red, or I don't know, your school's colors orange, the things that make that orange deal with the electrons inside the pigments and dyes put inside that t-shirt, and that's what we're going to talk about. What actually happens with those electrons is they jump from one energy level to the other, either going up an energy level, absorbing energy, absorbing light to do so, or jumping back down, releasing light. And all of it comes back to a little bit of chemistry. Don't worry, we're not going to be doing any weird stuff with chemistry. Just the basics of electrons and those orbitals and how they move, nothing you have to memorize. So moving on with that, I'm going to make these a little bit quicker. Light, and we'll get to this in a moment, consists of a very, very, very small portion of what we call the electromagnetic spectrum. It's a fancy way of saying all of the different kinds of light that could possibly exist. But these waves are always going to be absorbed or released from an atom's electrons as they move from one energy level to the next. And the main idea I've highlighted here in blue. If an atom, or if the electrons inside that atom, absorb a photon of light, they don't always have to, we'll talk about why, the electrons will take that energy and move up to the next energy level further away from the atom. It's kind of like if you're working for a big Fortune 500 company and you get a promotion, and now you can, no longer have to work on the 4th floor, but you get to move up to the 6th floor, right? It's a little bit more prestigious. It's a little bit higher up, whatever. Bad analogy, but it works. It's kind of like floors in a building are like energy levels around an atom. If you get demoted, then you might wind up going from the 6th floor back down to the 4th floor. In terms of an electron, that would mean that it gave off some energy, it gave off some light. And it turns out that those distances they move, we're not going to actually do the equation, so don't be confused by that HF right there. It's talking about the amount of energy that photon had. It's Planck's constant multiplied by the frequency. We're not going to do that equation, but we could calculate it. The idea is that if you jump from this energy level down to this energy level, you're releasing or emitting a photon of light. Let's just come up with a random number and say it's, I don't know, 500 megavolts or something like that. And then if you want to make the same transition going from let's call this the second energy level of the atom to the third energy level, it's going to require the exact same amount of energy to go from 2 up to 3 as it released going from 3 back down to 2. And that was the main idea I wanted you guys to see there. So, sorry, I lost my train of thought. I had to pause. Anyways, coming back. If you want to transition from the second to the third energy level, whether or not you're going up to the third energy level or back down to the second energy level, it doesn't matter. It's the same amount of energy that would be required. And you'll notice that part of this equation is frequency. And if there's a measurable frequency, there's a measurable wavelength. And so we're actually able to talk about it. We'll do it qualitatively. But you could calculate the exact amount of energy required to make an electron make that move. So these electrons, one of the things I want to start with as we jump into talking about how these electrons move around an atom is talk about white light. There's a couple of misconceptions out there. I've seen a couple of people write in a few places, several people, that white light is, light outside of our visible spectrum or any of those other things. It's not. It is comprised of every color of the visible spectrum that you can make up. So white light is your entire full rainbow. That's what happens when it rains and there's a lot of water vapor and moisture outside in the air, in the atmosphere. The white light coming from the sun passes through all of the water vapor in the atmosphere, and it acts like a lens, like a prism. This looks like, Pink Floyd's famous Dark Side of the Moon cover or album cover art. That's exactly what it is. White light entering that prism slows down a little bit and it spreads out. We'll talk about that phenomenon a little bit later. but it spreads out into its component colors, and that's where you get the full rainbow from. So white light is comprised of every single color that is there. When an atom is hit by that white light, this is why that was important. When it's hit by that white light, whether or not it's coming from the light bulb in your ceiling as you're watching this video, or maybe the white of the screen that I have as the background right now hitting your t-shirt, that white light is comprised of every wavelength within the visible spectrum. It hits that object. Some wavelengths are absorbed. Some wavelengths are not absorbed. The wavelengths that are not absorbed are either reflected or re-emitted. We'll talk about the distinction between the two later, but they're just not held onto by the pigments and dyes within that fabric, within that cloth, within that pigment that was put in there to make it that color. And because it's not held onto, it's reflected back into your eyes. So, if we wanted to talk about, a wavelength of, or a photon of orange light coming in and hitting your Lincoln Way West t-shirts, if that atom could hold on to, or maybe it can hold on to and then temporarily loses, if it absorbs that photon of orange light, then it can make an electron jump from one energy level up to maybe another energy level. Let's label this energy level 1, energy level 2, energy level 3. If it jumps from the first to the third energy level but can't hold the electron in this position, then it might re-emit that electron and fall back down the way it came. And if it does so, then that little photon that goes screaming off into the distance might wind up falling into your eye, and you observe your shirt as being orange, or it falls into your friend's eyes and they observe it being orange. Just because you're not looking at something doesn't mean it doesn't have color. Obviously, it always has that color whether or not you're looking at it. But that's what I wanted you guys to get from this particular understanding of white light. It's why things have the color that they do. So again, it's the electron moving from position to position. The importance of this slide is the distance between those energy levels. And it's primarily going to be this statement right here. The longer the jump or the fall that electron makes, so if we go here from our first energy level at N1 all the way out, let's say to N5, they made that transition, sorry, right here. If we make that jump all the way out there, there's a wavelength of light that corresponds with that atomic distance. It's very, 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 very small. We're talking about nanometers, which is, let's put it in perspective. You have a full meter stick in our classroom that I miss, and maybe you miss. If you don't, I won't take it personally, trust me. A full meter stick is 1,000 millimeters. Well, a single millimeter on that meter stick is made up of 1,000,000 nanometers. That's how small these are. It's very, very, very small, which is why you can see the waves in the ocean, and you might be able to see some compressed waves in terms of explosions when we were watching some of those videos with our sonic boom stuff, but you will not see a wavelength of light. It is far, far, far too small. But the idea is that the further the electron travels, the more energy was required to get there. If you want to climb up, the flights of stairs in your home, it doesn't require a lot of energy. But if you want to go climb the flights of stairs in the John Hancock building, like they do every year, that's going to require a lot more energy because you're going significantly further. It's the exact same idea. I think even in the worksheet that I asked you guys to do for assignment 1, I compare it to potential energy with gravity that we already talked about from way back before we left. And so I make a nice little analogy there that kind of, I think, helps make this a little bit more tangible. Now, to put some colors with all of that, I've got this other individual slide here. I want you to notice that if you're moving from the third energy level down to the second energy level, that is going to represent a very, very small, now this is going to change for every atom, so these are just generic examples. It's going to represent a very low energy, label it LE, very low energy sort of light, not energetic at all. We'll talk about different kinds of light. But if you're making a further transition all the way down, in this case, jumping from the 5th energy level back down to the 2nd, here you only transitioned 1 energy level. Here you're transitioning 3 energy levels. It's going to represent a wavelength of light with significantly more energy, a shorter wavelength, which means a higher frequency, more energetic. We'll talk about more versus less energetic and how we know. I've got a good little, description of real life that I use all the time to help you understand which one's more or less energetic, red versus purple, violet, whatever you want to call it. But this is a good little visual resource to come back to, especially if you get in the habit of labeling it as low energy, low frequency, high frequency, that sort of stuff. This next slide, this is actually where we get into how we know the universe is expanding, how those CSI laboratories work and function, and how we know all of the things that we know about the universe around us. What we see here are two different, I guess you could say, spectrums, two different fingerprints of the atom of hydrogen. One is an emission spectrum, and the other one is an absorption spectrum. The emission spectrum are the wavelengths of light and energy that the atom of hydrogen, in this case, could not hold on to when light was shining on it. And it wound up releasing, 5 different wavelengths of light, one here in the violet range, one here in the blue to violet range, one that is definitely blue. This guy looks, I don't know, teal, aqua, whatever the heck those weird colors are that no one understands except apparently my wife does. I don't get it. And then one guy over here clearly within the red spectrum. So your emission spectral lines are wavelengths of light that it could not hold onto. Absorption spectral lines show every wavelength of light that could have been held onto, with the exception of the ones that are missing, right? The wavelengths of light that the atom couldn't hold onto. You'll notice that they overlap and match perfectly. But the idea is that hydrogen atom could hold on to most stuff. But what I want you to notice, and what we have noticed, is throughout the analysis of these different things, time and time again over the last, 50 years that we've had reliable spectroscopy, we have never seen hydrogen not release 5 different bands that are all at the exact same wavelengths and all the exact same distance apart. Every time we shine light on hydrogen and we analyze the light that it cannot hold on to, we get this exact same literal fingerprint of the atom of hydrogen every time without fail. It doesn't matter if it's a lab here in America or South America or China or Russia. It doesn't matter if we're analyzing hydrogen coming from our sun or the closest star to us, Alpha Centauri. It doesn't matter if it's hydrogen atoms that are emitting light from the Andromeda galaxy several 100 million light years away. Hydrogen always has this fingerprint every time we've ever seen it. And this is where we're actually able to tell whether or not things are red shifted or blue shifted. We talked about this a little bit in chemistry last year. I didn't teach chemistry last year. I have taught it in the past. But this is when you did your flame test, right? Copper gave you that really cool blue color when you lit the copper salts on fire. Strontium would have given you a little bit of a red color, barium green, sodium would have been a bright yellow. Either titanium or magnesium releases that really bright white color that you guys are familiar with seeing from last year. This is why and how you get those very specific colors for all of those different things. So that's where this is coming from. This is also going to be exactly how we know whether or not things are moving towards us or away from us using the Doppler effect. All coming back to Doppler. The absorption lines always occur at the exact same wavelengths, the exact same distances apart every single time we've ever seen them. So if something is red shifted, you'll notice we have the exact same bands that we always had, right, here and in the lab. They show up in the exact same distances apart, but in this case, they have moved over just a little. I should pick a spot that's not red. They have moved over just a little bit. Now we could actually put down like a little, not put down a ruler, but we can use software to measure how much of a shift that is, and based on how much of a shift it is, it will actually tell us how quickly the object is moving away from us, in this case, because this line was red shifted, or towards us, because you'll notice this one is blue shifted. So if I clear all of those and draw a line, hopefully straight down, that really was not that straight. Awesome. You should notice that this one was blue shifted. So this light being emitted from this particular object here, as I make the worst arrow I've ever made in my life, light coming from that particular object in that third example down there at the bottom is blue shifted. It's coming towards us a little bit. Those wavelengths are getting bunched up. You get shorter wavelengths, higher frequency, more violet light. We'll talk about that a little bit more, but that's how we know when we look out into the universe that things are moving away from us. The vast majority of things are moving away from So this slide right here, I'm going to ask you to hit pause real quick because this is a great refresher of everything we just talked about. If you have these key concepts, you're good to go. So how do these two kinds of waves compare? Sound and light, good old-fashioned Venn diagram, and this is going to get into our last bit on the electromagnetic spectrum. So both sound and light act as waves. They have measurable frequencies and wavelengths. They both undergo or can be impacted by the Doppler shift. If the observer or the source of sound or light are moving, you can have apparent changes in frequency and wavelength. Sound specifically is a longitudinal pressure wave. It has to have a medium to travel through. Changes in the Doppler shift affect the note being played, and it goes about 340 meters per second in air. Separately, light is a transverse electromagnetic wave. It's a scary word. Don't be worried about it. It's okay. It does not need a medium to travel through, which is really good because there's nothing between us and the sun. And if it needed a medium to travel through, no light from the sun would reach us, and we would all freeze to death and die, and that would be kind of not ideal. It does not need a medium to travel through. Doppler shifts will affect the color of light, and it travels at a ridiculously fast pace, 300 million meters per second. Now, two more things they have in common. The source of all of these waves, the source of every wave ever at all, is a vibration of some kind. Sound is your vocal cords or my vocal cords in my throat vibrating as I push air through them, causing my voice to sound the way that it does. A tree falling in the forest is going to shift those air molecules around it. Yes, it produces a sound. No, you don't have to be there to hear it. That's a really annoying question. It's a vibration. That's all it is. Light is the same thing. It's electrons that are moving, shifting from energy level to energy level. Here's a really cool one, though, and this is one that a lot of people don't think about. There are sounds that you can't hear. Infrasonic sounds and ultrasonic sounds. Really, really, really good example of this is a dog whistle. A lot of times, if you've ever heard or watched dog trainers, they'll have a little whistle they'll keep blowing into that the dog can hear and react to, and you can't. Oftentimes, my pets growing up would pop up as they're relaxing on the couch and chilling and freak out because something was going on. No, it's not ghosts, probably. It's probably just that they heard a sound that you couldn't hear because their hearing is significantly better. So just like there are sounds that you cannot hear, even actually going back, a lot of you guys, to bring it closer to home, a lot of you guys like to screw around with this frequency generator apps in the classroom. I've noticed people doing that in the past where they'll turn it on at a really, really high frequency so that the teacher can't hear it because we're old and have damaged, I know I've damaged my hearing from all the concerts I've been to. So we'll turn it up to where we can't hear it, but some of the kids in the class can. It's sometimes funny, but most of the time just really annoying. So just like there are sounds that we cannot hear, there is light that you cannot see. Our window into the universe biologically is really, 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 really small, which is why we use technology to help us. The light is made of really, really, really small bundles of energy. We'll talk about this more later, called photons. They all fall on part of the electromagnetic spectrum. They're all versions of electromagnetic radiation or waves. Now, don't be afraid of the word radiation. Radiation literally just means anything that radiates outward. There's good radiation, there's bad radiation. I used radiation tonight to reheat my leftovers in the microwave because I was too lazy to cook. Even if you are cooking, you're using radiation over an open heat or open flame on your stovetop or your grill outside. That's radiation, heat. It's a version of electromagnetic radiation. It's an electromagnetic wave, and we'll talk about all of them here right now. Now, you don't need to know all of these specifically. What I do want you to understand is we're going to start with the least energetic and harmful and work our way all the way up. So the full electromagnetic spectrum encompasses everything that you see here on this slide. What you observe in your everyday life, Roy G. Biv, the rainbow, that thing you talked about back in junior high, that is less than 1% of all of the light that exists in the universe. All of the light that we have ever observed with all of our technology, we can actually see with our own eyes, less than 1%. It's a very, very, very sliver of the entire spectrum. So starting with the weakest kind of waves, the kind of waves that are literally everywhere. We're using them right now to communicate. If you're using Wi-Fi, you use them on your cell phone when you're trying, 25 minutes into this video, you're probably super bored, you're Googling something on your cell phone, you're using radio waves. These are the lowest energy, longest wavelengths. The wavelengths of these waves can be anywhere from a millimeter all the way up to 10,000 meters. Your AM radio waves that go super, super, super far in terms of broadcasting distances. Sometimes they have wavelengths so long they can literally wrap around a mountain, which is why they're able to travel that far. This is the kind of radiation that apparently some people are freaking out about with 5G and all sorts of weird stuff, but please don't. Radio waves have wavelengths so long they literally cannot interfere with the human body. In the last 40 years of cell phones being around, there hasn't been any research stating that the prevalence of brain cancer has gone up because of having cell phones next to your face as you're talking on them. They're fine. And if those studies do come back or do come up and they find those things, I'll take that back, but they haven't yet. We're 40 years into it. So radio waves, harmless. We use them all the time. Fantastic for communication. The next step up would be microwaves. This is a kind of radio wave, but it's a really, really, really energetic radio wave. It has wavelengths that are going to be a little bit shorter. Those wavelengths are short enough to where they can actually get into the molecules that make up your food in this particular case. And instead of irradiating your food, don't worry, it's not actually your food that absorbs those waves. What absorbs them are the water molecules. And it causes the oxygen hydrogen bond in the water molecule to stretch and compress. Crest trough, the whole wave action, it literally causes it to stretch and compress. And as that water molecule is sitting there shaking, vibrating, oscillating, it generates friction. And that friction is what warms your food. That's it. That's why things get dried out after a while, is because they move so much that they eventually evaporate up and off the object that is in there. It's also why there's that weird little mesh thing that allows you to look inside a microwave. You're not going to get brain cancer from watching your food, sitting in the microwave. That mesh is actually there to keep the microwaves inside the microwave. The wavelength of those microwaves is too long for them to be able to get out and through that little wire mesh. But notice visible light can get in and out because visible light is more energetic. We'll get there. Anyways, so moving up in terms of energy, we had radio waves and then microwaves, which we use for cooking food. Radio waves are harmless, they're everywhere. Infrared light. Infrared light is going to be a little bit more energetic than your radio waves. It's going to have a little bit more capacity in terms of harming you, but not much, because you feel it all the time. Infrared radiation is literally just heat. It's body heat. It's the heat from your stovetop that can cook your food, or your grill outside. This is a version of radiation. We can't observe it, but there are actually several animals in the animal kingdom that can. Some reptiles are really good at sensing infrared radiation, sensing body heat. And that's all any of this is. I felt this today as I was sitting there grading all of your homework assignments. The laptop was generating a lot of heat from all those electrons flying through it from being on so long. And, my thighs got a little red, a little hot. You can get burnt, sure, but it's going to take a lot of infrared radiation in order to harm you. The next one that is on the spectrum, notice we had infrared. Well, next is red. Right? As we get a little bit more energetic, you get the entire visible spectrum. The visible spectrum comes after infrared radiation. Again, it is a very, very small, thin range from 400 to 700 nanometers in wavelength. Very, very, very small waves. But infrared means below red. Slightly more energetic than that would be red, orange, yellow, green, blue, indigo. And then the most energetic on the opposite end of that spectrum is violet, which should make sense because what's a step beyond violet other than the word that literally means above violet? More energetic than visible light is going to be ultraviolet light. I'm very familiar with ultraviolet light because I've already, in this very short summer that we've had, spring, whatever the heck you want to call it. I don't even know what summer or what season it actually is anymore. This can get into your cells and literally break them apart. That's what a sunburn is. I'm very familiar with it because all of my ancestors apparently hid from the sun. But a sunburn is literally just very, very smaller than radio waves, smaller than your 5G radiation, smaller than visible light. These wavelengths are so small that they can get into the chemical bonds that hold your cells together and break your proteins, break your cell walls apart, kill the cell in general, and they fall off. That's why your skin peels when you get a really, really bad sunburn at the beach or whatever it might be. It's shedding layers of dead skin that were fried by radiation. Unfortunately, if that happens too often, you can have the wrong break in the wrong molecule at the wrong point, and if it's a part of the DNA that codes for cellular replication, it could ruin the cellular replication process, and now you have melanoma. Obviously not ideal. But these are very, 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 very energetic particles. Literally means above violet. That was the main idea of the slide. Again, infrared radiation damage. Might not notice it, but it's always there under the skin. That's kind of creepy. X-rays, even more energetic than ultraviolet. These are so energetic, not only can they get into your cells and ruin them by breaking them apart like they always had. This is why they put those lead vests over certain parts of your body, or why the lab tech hides behind the wall when they do an X-ray. But these have so much energy that these waves can go through all of the organic matter in your body, and the only thing they really can't get through is the much, much, much more dense bone. They're reflected off of the bone, and that's what you see in these photographs, right? So these wavelengths are so short that they can pass through all of that soft tissue, make it through the human body, and just be reflected off of the bone. And that's how we're able to see whether or not you've broken something. These are still incredibly dangerous in high doses. Don't panic by going and having an X-ray. You can get somewhere up to I think it's 300 X-rays a year before your chances of getting cancer change by 0.01% or something crazy small like that. You're fine. I know it's about 300 because what was it? One CT scan that my mom was having on her neck for all of her neck surgery issues. They always said, oh, it's about the same as 300 X-rays. You don't want to do this too often in a year, but you'll be fine. So, there we go. Really, really dangerous in significant doses, but really, really, really small in terms of their wavelength. So small, we get actually a new metric prefix, pico. 10 to the negative 12th. This is 1,000 times smaller than a nanometer, which remember was 1,000,000 times smaller than a millimeter. Really, 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 really small stuff. Here's what you might see out in the universe with the naked eye. Here's the same shot from a similar location in X-ray light. It's everywhere. Just because you can't see it doesn't mean it doesn't exist. It's just outside our field of view, like a dog whistle. Gamma radiation is the last one I'm going to talk about. This is where I'm going to end it. Gamma radiation is obviously the highest frequency light. All of these have been versions of light, visible or invisible, doesn't matter. It has the shortest wavelengths, the highest amount of energy associated with them. This stuff can travel through pretty much any sort of material at all. This is why bomb shelters in the Cold War era were required to be so thick in terms of walls of concrete. You either needed lead or feet in terms of the thickness of your walls of concrete in order to stop all of the gamma radiation from getting into your bunker. No, it doesn't do this. That would be awesome. It's just not how that goes. Instead, what it would literally have done to Bruce Banner, it would have just killed him. I'm not going to encourage you to Google it, but it is radiation poisoning, and radiation sickness is pretty nasty. It literally causes the flesh to melt off of your skin because it kills everything so fast. It's not fun, but that was your electromagnetic spectrum. Now, for the homework assignments, you've got 2 of them today or this week. No gizmos. There wasn't a good one that didn't deal with stuff we weren't going to be talking about. I want this to be mostly conceptual, with the exception of our wave equation. That's the only math you're going to be doing. It's literally speed of light is equal to wavelength multiplied by frequency. That'll be assignment 2. Assignment 1 is conceptual, this sort of stuff, straight from the notes. If you have questions or concerns, please do not hesitate to reach out before the deadlines. That way I can get something out to address them. I'd love to be able to do that for you guys. That was about it. If you watched the whole thing, cool, congrats. Appreciate it. I don't think anyone has yet. See you guys.